wave. But what does it mean? Well, let's begin by simply looking at the cosine of kx. I'm defining k as 2 pi divided by lambda, where lambda is the wavelength of the wave. Here is the wave, and the wavelength is the distance between two successive peaks. So, we can rewrite the cosine of kx as cosine of 2 pi over lambda times x. What happens when x equals lambda? Then the term becomes cosine 2 pi, and that equals 1. And so, for every x is 2 pi, that is 2 pi, 4 pi, 6 pi, and so on, the wave will have completed one complete wavelength and will look something like this. That is known as a standing wave. It doesn't go anywhere. If we now take the second part, cosine kx minus omega t, this is what's known as a travelling wave, because the wave will actually move at velocity v to the right. I'll tell you what v is in a little while. Where do the peaks fall in this wave? Well, the wave will reach its maximum amplitude when kx minus omega t is 0. Because when kx minus omega t is 0, cosine of 0 is 1. And that's the maximum amplitude. Unless, of course, you have this a amplitude term in front of the whole thing. So when kx minus omega t equals 0, that is the same as saying kx equals omega t, or x divided by t is omega divided by k. But what is x divided by t? X is distance, t is time, and distance divided by time is velocity, v. And so this moving wave is travelling to the right with a velocity given by omega over k. But what is omega? Omega is the velocity in radians and is 2 pi times the frequency. What is k? K, as I've already said, is 2 pi over lambda. So omega divided by k is 2 pi f divided by 2 pi over lambda, which is simply f lambda, which is the frequency times the wavelength. Frequency times wavelength is the velocity. Frequency is the number of waves that pass a particular point per second, and lambda is the wavelength of each distance from crest to crest. And so f times lambda is the number of waves which pass per second multiplied by the wavelength of those waves, and that gives you the velocity per second. We can also say more about k. K is 2 pi over lambda. But from my video on the reason for quantum mechanics, you will see that we derived the formula lambda equals h over p, where p is the momentum. So k is 2 pi divided by lambda, which means is divided by h over p, and that is simply p over h bar, where h bar is a new version of Planck's constant, h over 2 pi. And that means that p equals k h bar. H bar is a constant, so k is in essence a measure of momentum. So in this formula for start, it equals g to the I kx minus omega t. We can say that k is 2 pi over lambda, but it is also p over h bar, and it therefore gives us an indication of the wavelength of the wave and the momentum of the wave. Omega is 2 pi times the frequency, and thus gives us an idea of the frequency of the wave, and the velocity of the wave is omega divided by k, and that tells you how fast the wave is moving to the right. Hello, today we're going to look at the double and single slit experiment and diffraction gradients. We'll start with the double slit experiment. Young's double slit experiment was supposed to be the definitive proof that light was a wave, not a corpuscle or a particle. Then along came Einstein and showed that light could behave both as a wave and as a particle. The principle of the double slit experiment is that if we take a piece of board with two slits in it, and we have the ground underneath, and over the two slits we put some dry sand, then you would expect the sand to filter through the slits and form a pile underneath the two slits. So these are piles of sand as the sand falls through. That's what you expect with sand. Do you get the same sort of thing with light? Well, let's just turn it round so that the slits are now like this. We're going to have a source of light, which we call a monochromatic source of light. That means it's the same colour, red or green. You have to have it a single colour, otherwise you start to get the colours of the rainbow being filtered out, and that upsets the experiment. So you want a single source of light so that the same light goes through both slits and comes onto a screen here. Now what do you expect? Well, in the same way as the sand forms piles underneath the slits, you might expect that the light coming through here would form a, as it were, pile of light. So this is really a measure of intensity in this direction. So what we're seeing here is the brightness of the light on the screen. And similarly, opposite this slit here, you might again expect to find an intense light in this region, probably a bit dark in the middle, and then falling off to darkness on both sides. And that is certainly true. It's broadly true if what you do is to close off one of the slits. So if you close off one of the slits, you will actually get, broadly, that kind of impact. You'll get a bright area on the screen. But if you open up the second slit, and indeed if you close off the top slit, you will get the bottom effect. But if you open up both of the slits, what you actually get, well, let's just draw this again. Here are the double slits. Here's the monochromatic single source of light, so the same light goes through both slits. There's the screen. And what you actually get, opposite the sort of central point, is you will get a bright area, but then it falls off to an area of darkness, then an area of light, then darkness, then light, then darkness, then light. And similarly on this side, light, dark, light, dark. And these are fringes. So on the screen what you're actually seeing is brightness, dark, bright, dark, bright, dark, bright, dark, bright, dark, bright, dark, all the way down. Those are called fringes. In other words, you get darkness at a point where previously you got light. So how is it that if you get light with one slit and more light with a second slit, with both of them open, you actually get darkness where previously with only one slit you got light? How can that be? The answer lies in the nature of waves. It's called superposition. Imagine that you drop two stones into a pond, a still pond. And this is where the two stones fall into the pond. They will create ripples, or waves, which will spread out across the pond. And it's the point where the ripples overlap that you get what's called interference. That means that you've got crests of one set of ripples meeting crests and troughs of another set of ripples. And what happens in those circumstances? A crest meets a crest. Here's a crest coming this way, meeting a crest from this set of ripples. They will in fact pass through one another and go out the other side, but when they overlap, you get what's called superposition. You get a double crest. Similarly, if you've got a trough from this stone meeting a trough from this stone, again you get superposition, a double-sized trough. But if you get a crest from this set of ripples meeting a trough from this set of ripples, you get flat water, assuming that the amplitudes of the two are the same. So we have to get two identical stones and throw them in from the same height to get the same amplitude of waves. They cancel out. And it's that cancelling out that is the reason why you get sharp fringes at all of these points here, because the waves somehow manage to cancel each other out. That's the principle of superposition. On the other hand, if the waves reinforce one another, like this, then you get a double crest or a double trough. Now, what is actually happening when a wave goes through a slit? You'll notice in the diagram I drew that I showed that the light seems to spread out of it. Well, let's take waves, what we call plane waves, coming from our source. These are plane waves. These are rather like the waves of the crest on the sea. So if these lines each represent the crest, then the wave looks something like this. So that each of the lines, there'd be another line here, represents the crest of the wave, and the distance between the lines is called the wavelength. Now what happens when plane waves meet a gap where the gap is broadly the same size as the wavelength? What happens is that gap becomes what's called a Huygens force. I've probably not pronounced that properly. It's a Dutch name and you need to be able to get the right intonation. But I'll call it a Huygens force after the man Huygens. And eventually it becomes a separate source of waves. And so you get waves spreading out in all directions, rather like the ripples on the pool. They'll have the same wavelength, but that wave will move in this direction. This wave down here will move in this direction, so it's moving down there. This one's moving up in that direction. The wave spreads out in all directions. That's called diffraction. As the plane waves come to the slit is broadly the same width or the same width as the wavelength, then you get this diffraction effect and the light or the waves spread out. By contrast, if the slit is too large, here is the slit, here are the waves coming in this direction. If the slit is too large, the waves simply pass through. They don't even realise that there's a slit there. On the other hand, if the slit is too small, then the waves come along in this direction and they simply reflect and bounce back in the other direction. They don't realise there's a slit to go through. So if it's too small, they reflect. If it's too big, they go through undaunted. But if the slit is about the same size as the wavelength, then you get this process called diffraction. So what happens with the double slit experiment? Here's the double slit. Here are the waves coming along. And what they're going to happen when they get to these slits, they're each going to form a Huygens force. So rather like the stones in the pond, you're going to get two sets of ripples from these two slits. And where the waves overlap, you're going to get interference. Where you've got double crests or double troughs, you'll get constructive interference. In other words, you will get double-sized crests and double-sized troughs. Where you've got a crest meeting a trough, you're going to get what's called destructive interference. In other words, the two will cancel out and you will get darkness. I should explain that for light, each of these slits has to be kind of nothing more than a small pinhole with the same gap between them, so the distance between them is very, very small, and the holes themselves are very, very tiny. in order that, as I said, the pinholes have to be broadly the same wavelength as the wavelength of the light. But in order to understand what's going on, we need to magnify this significantly. So let's assume that these are our two slits, and they are a distance d apart. And although the waves are going to move off from these slits in all directions, I am for the moment going to consider a wave which moves off in that direction from the two slits. That's going to be at an angle theta to, as it were, the horizontal. Now I drop a perpendicular down to this line here, and we know that this distance here is d. That's the gap, the thickness of the slit itself. And what I want to know is what is x, which is the distance from here to here. Well, if this is theta, then this angle here, by geometry, is also theta, which means that x over d is sine theta. X over d is sine theta, which means that x over d equals sine theta, x equals d sine theta. That's just pure geometry. But what happens if x is equal to lambda, i.e. the wavelength of the waves, or n lambda, where n is any whole number, integer? If that's the case, then the waves will be in phase, these two waves will be in phase, and you will get constructed interference. What I mean by that is that this wave will move in this direction like this. This wave will also do the same, but if this distance x is one complete wavelength, then you can see that from this point on, this wave is wholly in phase with this wave up here. The two are exactly in phase, because this distance here was one complete wavelength, or any number n, where n is a whole number of wavelengths, so that you're going to get constructive interference, because crest meets crest, trough meets trough. Your eye is up here looking at everything as it arrives. So that is the position for constructive interference. Crest meets crest, produce a double crest. Trough meets trough, produce a double trough. That's the position of constructive interference. So if x is d sine theta, but x equals lambda or n lambda, then the condition for constructive interference is that n lambda, which is x, is equal to d sine theta, from this formula up here. And that is the condition for bright fringes. And I think you can see that if x is equal to lambda over 2, in other words half a wavelength, or 2n minus 1 times lambda over 2, which means an odd number of half wavelengths, because obviously an even number of half wavelengths is a number of whole wavelengths. So an odd number of half wavelengths, or just one half a wavelength, then this distance here would only be half a wavelength, and consequently these waves would actually be completely out of phase. So that would be the condition whereby a crest would meet a trough to produce nothing. So that's the condition for destructive interference. In other words, 2n minus 1 times lambda over 2, this condition here, is equal to d sine theta. And that's the condition for dark fringes. This is light fringes because x is a complete number of wavelengths. This is condition for dark fringes, destructive interference, because x is an odd number of half wavelengths. So let's now imagine that we have our two slits. Remember, these are essentially very small pinholes separated by less than a millimetre, but I'm drawing them much larger so that you can see what's going on. And we have a screen over here, and the screen is going to have interference patterns. This is we are drawing intensity, in other words, in this way, that shows the brightness on the screen. The brightness falls off as you get further and further out. Fringes go reducing brightness, but they are still very visibly bright dark fringes. And what we're going to do is we're going to look at the first fringe, the first area of brightness. There will always be one bright fringe opposite the double slit, but we're going to look at the first fringe above the central fringe. And that's going to be at an angle theta.